The network was recovered in 4 minutes and 37 seconds. That was the fastest recovery on record for this segment, faster than any previous incident, faster than any benchmark, faster than what the hardware should have been capable of. Everyone in the room was relieved. Elena was not. A network that recovers faster than it should is not a network that got better. It is a network that stopped reporting accurately. And what he had stopped reporting, what was hidden underneath the clean metrics, was about to take Zone 4 offline for 11 hours. Today, we are going to talk about how AI recovery systems can produce accurate reports of inaccurate situations, and about the engineers who learn to read the speed of a recovery as a warning sign rather than a resolution. AI-driven incident response systems are built around a single primary objective: restore normal operations as quickly as possible. When a segment fails, the AI identifies the failure, reroutes traffic, isolates the degraded component, and monitors the recovery metrics. When those metrics return to baseline, the incident is closed and the resolution is reported. The system is optimized for resolution speed. It reports what the metric says, and in most cases, the metrics are accurate. Gartner's 2025 Network Automation Report found that AI-driven incident resolution now averages 68% faster than human-managed responses across enterprise environments, with accuracy rates above 94% for standard failure modes. But there is a class of failure that AI recovery systems were not designed to detect, because it does not look like a failure. It looks like a success. It looks like a fast recovery. And understanding why a fast recovery can be more dangerous than the slow one is the thing Elena had spent 3 years learning to say. AI recovery reporting works because network recovery produces consistent telemetry patterns. Latency returns to baseline over a predictable time window. Packet loss drops in a characteristic curve. BGP routes will converge in a sequence that matches the network's established behavior. The AI knows these patterns. It has been trained on them. And when the metrics match the pattern, the recovery is real. The problem Elena noticed was not that the metrics were wrong, it was that they were right too fast. When Elena's network recovered in 4 minutes and 37 seconds against a historical baseline of 9 to 14 minutes, she was not looking at the exceptional AI performance. She was looking at a network that had lost a subsystem during the failure event and was now reporting the metrics of a smaller, lighter topology as if they represented a full recovery. The AI was not wrong. The metrics it was reporting were accurate. The topology it was reporting them from was incomplete. The AI's recovery model is optimized for accurate reporting within its training data. It does not flag statistical outliers in recovery speed because recovery speed was not a failure signal in its training data. Fast recovery was always a good outcome. The human diagnostics that Elena was applying, comparing the current recovery speed against the full historical distribution for this specific segment, is not in the AI's model. It is in our 3 years of incident history. That is the layer the hybrid model has to include, not just monitoring recovery, monitoring the speed of recovery as a diagnostic signal in its own right. Elena pulled the topology comparison herself. pre-failure against post-recovery. The active component list was shorter by one entry. A storage subsystem in Zone 4 had dropped off the network during the failure event. The AI's recovery protocol had not restored it. It had rerouted around it. The remaining component had normalized their metrics under the reduced load. The AI had reported recovery. Technically, it had recovered everything that was still in its topology model. The subsystem that had just dropped off was not in the model anymore. Elena spent 40 minutes building the case that a closed incident needed to be reopened. The storage subsystem had been running at 94% terminal capacity for 6 hours before the initial failure event. The failure event had been caused by the subsystem. It had been caused by a separate interface degradation, but the failover had rerouted load to the already stressed subsystem, which had then exceeded its terminal thresholds and dropped off the network. The AI had recovered the interface. The subsystem that had silently exited the topology under terminal stress was now running in a degraded state, outside the monitoring model, accumulating errors. Without intervention, it will fail completely within 2 to 4 hours. Elena escalated at hour 2. Zone 4 was replaced in the controlled maintenance window at hour 3. The subsystem was restored, terminally managed, and reintegrated into the active topology. The intervention prevented an unplanned 11-hour outage. The 3 skills she used. First, she knew the historical recovery speed distribution for that segment. Second, she could read a topology comparison and identify a missing component. Third, and most importantly, she had the standing to reopen a closed incident that every instrument said was resolved. None of those skills are in the AI's model. All of them are acquirable. And right now, very few organizations are deliberately building them. Elena's value in this situation was not that she caught something the AI got wrong. The AI reported correctly. The metric it measured were accurate. The resolution it declared was legitimate within its model. Her value was that she could read a correct AI report as a diagnostic signal and understand that a statistical anomalous recovery speed was evidence of a topology change the AI had incorporated into its model without flagging as significant. The framework Elena was applying is not complex, but it is not automated. First, how does this recovery speed compare to the historical distribution for this specific segment? A recovery that is faster than 2 standard deviations from the mean is a topology event, not a performance improvement. Second, is the post-recovery topology identical to the pre-failure topology? A shorter component list is evidence of masking failure, not a clean recovery. Third, what was the terminal and load state of all components at the time of the initial failure? A component that was stressed before the failure is a candidate for a max degradation after the recovery. The engineers who will matter most are not the ones who can configure AI monitoring tools. Those are table stakes. They are the ones who can read an AI report as a diagnostic instrument, who understand not just what the AI is telling you, but what the AI model is not built to say, who can look at a 4-hour-minute recovery and ask, what changed in the topology that made this possible? That question is not in the AI's training data. It is in the 3 years of incident history. And it saved Zone 11 hours of unplanned downtime. The networks of 2030 will have AI that is better at recovery reporting than anything Elena was monitoring. They will still have masking failures because the underlying physics of terminal degradation and topology-masked load shift will not change. The failure mode is not a software problem. It is an architectural reality of high availability network design. What will change is whether organizations have built the analytic framework to detect masking failures systematically, or whether they are still depending on individual engineers who are prone to notice that a recovery was too fast. The 2025 Forrester Research Report on AI-managed infrastructure found that 61% of post-incident reviews in enterprise networks identified at least one topology anomaly that was not flagged by the AI recovery system. In most cases, because the anomaly was in the recovery behavior itself, not the network metrics. The rules being created right now are not the ones that watch recovery dashboards. AI does that. They are the rules that build and maintain the diagnostic frameworks that sit above the recovery reports. The analysts who define what anomalous recovery speed means for each network segment. The specialists who run topology verification as a standard post-recovery protocol. The engineers who translate 3 years of incident history into systematic diagnostic criteria that the next generation of engineers can apply without having been in the room for the original incident. Elena's 3 years of knowledge should not live only in Elena. The organizations building better are the ones that know that. Zone 4 ran without interruption. The subsystem was restored in a controlled 11-minute window. The terminal management protocols were updated. The AI's monitoring model was reversed to include subsystems heat correlation in its post-recovery topology checks. Elena filed one line in the incident note. Recovery speed, statistical outliner, topology masking, subsystem degradation identified and resolved. What she did not file, because there was no field in the incident report for it, was a question she had asked when everybody else was satisfied. The network recovered in 4 minutes. That was the warning. She was the only one who read it that way. If Elena's story gave you something, drop a comment. Has the system ever reported success while something was hidden underneath? I want to know what you saw that the metrics didn't, because those are the stories that should be documented, and most of them never are. Next week, an AI system that predicted a network failure correctly and predicted the failure window incorrectly by 6 hours. The engineers who recalculated the failure timeline manually escalated to the right team 4 hours before the AI said to, and prevented the failure that the AI had predicted but misscheduled. The argument, predicting that something will fail and predicting when it will fail, are different scales. AI is better at the first. Humans, in some situations, are still better at the second. Subscribe so you are there. And if this gave you something to think about, share it with the engineer on your team who reads dashboards differently from anyone else in the room. That person is more valuable than most organizations know.